Alexander Gegu from University of Portsmouth, who will be talking about introduction to explainable artificial intelligence. So please be aware, this session will be recorded in Zoom in British Computer Society, also in Teams in our channel. Okay, yeah, please.
Good afternoon, everyone, from me as well who's here. Maybe good morning, good afternoon, or good evening to anyone who's attending virtually at in different time zones today. Of course, I'd like to thank first, the host of these events, Solent University in Southampton, and Professor Callum Bennett for inviting, but also the British Computer Society. As Callum already said, I'm currently with the University of Portsmouth. The School of Computing, not too far away from here, and I'm Associate Professor in Computational Intelligence. There's a slight problem with the slides, by the way. Let me just see. Oh, good. I've sorted it out. So this is the outline of my presentation. Initially, I'll talk very briefly about what I'll describe as AI characteristics, desirable characteristics, and what you may have come across. Bias in AI systems. And then the rest of the presentation, I'll talk about different aspects of what we call explainable AI, in particular, taxonomy, types, formats, challenges, maybe some solutions. And at the end, I'll just present a generic concept, and I'll finish this presentation with a few books, which I'm currently using for a master's module explainable AI. As part of a MSc course in artificial intelligence at the University of Portsmouth. And my plan is to talk for about 30 minutes, maybe not more, so we can have enough time after my talk for discussions or any questions, any comments, which I think would be also quite interesting for everyone who is attending this seminar. I'm sure you'll agree with me if I tell you that AI has had very kind of significant advancements over the last 5 or 10 years, especially in terms of what we might describe as predictive performance. Now AI models can resolve tasks, typical machine learning tasks such as classification and regression with much higher degree of accuracy. And that is great. And AI is already used in many different areas with a lot of success. However, I'm sure you've also heard that there are a lot of concerns about some recent developments in AI. And some of these concerns have also been shared by some of the AI pioneers and very established authorities. And people have been talking about maybe lack of sufficient level of responsibility or trustworthiness, or safety, or even reliability in current AI systems. And again, the main reason for that is that many of the existing machine learning models, which are used as AI systems, or as part of AI systems, they're like black boxes, and they don't provide any kind of explanations about the recommendations or decisions that they make. And a lot of people are happy about that. So for this reason, a lot of communities around AI machine learning have started to address this problem recently. And with my experience as associate editor of several international journals, including 2 IEEE transaction journals, I have to say that over the last few years, maybe every 3rd or 4th paper submitted for possible publication in these journals has something to do with explainable AI or interpretable machine learning, which quite often is used as a synonym, although it's not exactly the same. So what are the ways to actually address these problems, as mentioned here on this slide? The first group of 4 bullet points. Again, how to make AI fairer, more transparent to the user, interpretable, mainly by experts, but also explainable to other people, stakeholders, and non-experts. So generally speaking, the second group of things, which you see here on this slide, is a way to address the first group of things, which is on this slide. And you may have heard on the media of the recent years that a lot of kind of established organizations and institutions like the European Union and NATO and the British government
Sorry to interrupt. We have lost the sound on the Zoom. Please could you ask the speaker to unmute and also to turn the volume up if possible, please. Thank you.
Yeah. Is this mic working?
Can you hear now?
I can hear you, Neville,
Right.
Okay.
but the speaker was much softer voice than you, or different position,
Right.
physical position.
It's got-
Okay, I'll try to speak up. I also have something like a cold, so I'll do my best. So again,
thank you.
quite often,
Thank you.
when we go to the real world and we want to somehow identify some relationships in the real world using, let's say, an AI model, and if there's some bias in kind of this real world, which often there is, this is then reflected in the data, maybe in terms of the labels, which may be biased as well. So this data bias then becomes encoded in algorithmic bias. In other words, if you use an algorithm to then construct or learn a model, it's also there, it's embedded in the model. And then this bias could potentially be uncovered fairly easily by what we call explainable AI. In other words, we can use explainable AI to mitigate as far as possible real-world bias and make AI systems kind of more ethical and fairer and more user-friendly. Moving on now to the XAI topic. First, I'll say a few words about taxonomy, which exists. In terms of the dataset application scope, we can have global or local explanation methods. For example, global methods are ones which try to explain the whole data set, whereas local methods are the ones which usually explain individual instances or groups of instances. In terms of machine learning models that we use to explain, we've got two main groups, interpretable and black box. The first group is much smaller, and it includes methods like linear regression or logistic regression, and also some kind of decision-based methods like decision rules and decision trees. And they're usually interpretable because they've got some internal structure which can help us explain these models. For example, we've got these coefficients for the linear regression models, and we've got all these kind of nodes for decision trees, splits, rules, and all that stuff. However, black box models, I mean, I wouldn't say they don't have an internal structure, but it's so complicated that it doesn't make sense, and it's very difficult to explain. That's why we call them black box. And in terms of model explanation methods, again, we've got either specific or agnostic. The model explanation methods which are specific are the ones which are used together with interpretable machine learning models because they're specific to the internal structure of these models. Whereas the agnostic methods, I mean, they don't care about the internal structure. We can use them, and we usually use them for black box models. But in some cases, we may decide to ignore the internal structure of the interpretable models, assume it's not there, and still apply agnostic methods to these models. And there's one special case, which is neural networks. They've got internal structure, but it's so complicated that actually we can't make too much use of it. And we still use specific models which somehow kind of make references to different parts of this structure to explain what they try to do. Moving on to the next slide, we've got a few main types of explainable AI. Maybe I'll start calling this XAI, which is a very kind of broadly adopted acronym. So we've got this pre-model type, whereby we've got the data, then we've got some kind of explainable AI. In most cases, these are like different types of visualization methods, data visualization methods, and they've been around for many years. But I think that maybe some people from the XAI community have tried to somehow hijack them, and now they put them into this type of model. So once we visualize the data, then we can apply, for example, a black box model and then present this model to the user. We've got then the other second type, which is called in-model. We've got the data, and we assume that we can apply an interpretable model like regression-based model or decision-based model, which is explainable by itself, and then we present this model to the user. And then we've got the post-model type, whereby we've got the data, we apply a black box model to the data, then we try to explain this black box model using an explanation method, and then we provide this to the user. In terms of formats, there are many different types, but I've tried to group them into two main types. Again, the first one is what we call either what if or counterfactual explanations. And these are really very useful because they're about, let's say, alternative reality that we may want to build. But just imagine that you, for example, apply for a job, but your job application is rejected. You may want to know what you need to change in your application next time in terms of the input features to this model that you can use to tell you whether you'll be successful or not in order to be successful. So that's just one example that explainable AI is not just about explaining the actual reality, but it's also useful for trying to simulate alternative reality that we want. In other words, how maybe to flip the outcome of the model, if it's categorical, or to move it if the outcome is numerical in a desirable direction. And that's something very important because based on my experience until now, AI has been used mainly to observe the environment, recognize things, classify things. But how about if we don't like this environment and we want to change it for the better? Well, XAI can give you an answer. What you need to tweak in the input features and their values in order to obtain this alternative reality, to move the outcome in a desirable direction. And there's another group called example-based or constructive. Now, they're about the actual reality. In other words, quite often in order to explain something to a user from a model, the best way to do that is to take maybe specific instances and explain them rather than to explain the whole data set. What are the main challenges? Again, I've tried to put these challenges into several groups. The first one is evaluation. I think that although this field has been very extensively researched over the last few years, there's still not maybe kind of established evaluation methods as to how good explanations are. And this is a very difficult issue because it's something very subjective. What can be a good explanation to someone may not be so good to someone else. So therefore, we may have to think about different levels of explanation, maybe explanations which have more or less detail, depending on the preferences of the user, or explanations which may be aimed at experts or, general stakeholders, non-experts, respectively. Formalization, again, we still need to do more in terms of trying to formalize this approach to make it more academic, more mathematical, more systematic, because a lot of the explanation methods that exist are quite empirical these days, okay? With exception of maybe one or two. One of them is called SHAP, based on Shapley values. You may come across this. And the other one is called LIME. These two methods have become more popular because they're more systematic and they've been also implemented in different types of software packages. The other two things which we need to think about is adoption acceptance. I'm just talking about AI in general. Again, a lot of people are very enthusiastic about AI, but a lot of people were very enthusiastic maybe before the referendum, especially the academic sector. They thought, oh, we'll win the referendum, we'll stay in the Union, in the European Union. I don't want to be political, but what happened was exactly the opposite. So if you go in the wide open, you may see a lot of resentment, a lot of people who are not happy about recent developments in AI. And maybe they've got a reason. So we need to convince them. We need to make sure that AI is adopted better, it's accepted better, because then maybe we'll be able to achieve better things and we'll be able to maximize the benefit and minimize the potential risks. Other things which should be addressed are causality and reasoning. Well, these days, obviously, machine learning models, they work in a similar way. They take some kind of data, and then on the basis of the values of the input features, they try to do a prediction or classification for the target output. But very often, these kind of input features, they're not kind of causally related to these target outputs. This relationship is kind of more based on what we call association or correlation rather than causality. And for some areas, especially safety critical areas, like, let's say, transportation, aviation industry, healthcare, we need to identify these input features which are causal, because if you want to change things for the better, avoid any problems with patients or whatever, or even in defense and security, these days we know how unsafe the world is. And people are concerned if people start using AI to make decisions to whether to take an action against another country which might be an enemy. So what I was trying to say is we need to identify which of these input features are really causally related to the output and how you want to maybe tackle or address these causes if you want to change the output for the better. And finally, reasoning. Actually, machine learning is great, but I think that it's only kind of scratched the surface in terms of what we can achieve with regard to AI, and it's still quite limited. So if we want to make AI systems more sophisticated, more user-friendly, we need to start kind of expanding or complementing machine learning with machine reasoning, which is something much more challenging to achieve, but people have started working in that area. So learning is about extracting knowledge from data. Reasoning is about accumulating new knowledge from the knowledge that has been extracted from the data during the machine learning process. And sometimes this may be really, really very challenging, but if you think logically, we humans can do that very easily. However, machines still not do that very well. So let's see what happens. Now, there are a few slides which have the heading solutions, and I think that this is maybe hard to say, maybe like an overstatement. What I've tried to put in these slides are some kind of ideas, which are at a very conceptual level, but I won't go into too much detail because I want to leave more time for questions. Then I can come back to some of these slides if anyone from the audience has any more specific technical questions. Anyway, all these kind of ideas, maybe for addressing some of these challenges, are based around the same kind of overall concept, that maybe, explanations could be either facilitated or made more difficult depending on the structure of the machine learning model we use. And I'll try to argue that quite often, maybe we need to think, how to say, not just in terms of flat models, but also in terms of deeper hierarchical models within certain limits, because we need to be able to find some kind of balance between very rough flat models and very complicated hierarchical models to make sure that on one hand, we can explain the model, it's not too complicated, but also on the other hand, to make sure that it's not too kind of rough and too superficial. So I'll just say a few words about these slides. Again, here on this slide, you can see maybe two general classifications in terms of explainable models. For example, we can either try to do global analysis, in other words, look at all inputs and all outputs, because there may be more than one output, or local analysis, just look at individual inputs and outputs. but also we need to make sure that whatever explanations we provide, they have to be meaningful. And again, this particular context, we could identify maybe two main types of models. Simple structure models, which are called flat. And this is a term used in many other, well, kind of areas and by many journals and societies, where you've got all inputs and outputs, might say black box models, but also more complex structural models, which you might call either white box or gray box, where you don't have only external inputs and outputs, but also some submodels and connections between these submodels. Maybe I'll just say only a few words about this slide because it goes into too much technical detail. But anyway, it is just one illustration of that whole idea, how we can use this structural modeling approach, maybe which is based on graphs, to represent models. And again, we can maybe use this kind of graph-based approach to evaluate the complexity of this model in terms of levels, horizontal levels, vertical layers, or number of inputs, outputs, submodels, and internal connections, and then use edges and nodes to refer to these different parts of the model. And this is maybe, again, something which goes into more technical detail. I will not discuss in detail, but generally speaking, the main point is that we can distinguish two main types of models, again, in relation to explainability. And maybe macro models, quite often they're called flat black box with a single node. And this is just one kind of mathematical way of representing such a model with, let's say, 4 input features, the x's and 1 output target, the y. And then micro models, which we could also describe as hierarchical white box models with multiple nodes, whereby we can position these kind of separate submodels into different cells of this grid structure. So actually, the macro models usually provide what we can call shallow, concise explanations, which may be not sufficient for expert users. However, for non-expert users, maybe these explanations may not be sufficient, maybe have to provide what we call deep or detailed explanations through micro models. But again, in a language which is understandable by non-experts. And here on this slide, I've tried to somehow conceptualize maybe 3 different scenarios. In terms of the complexity of the model and the complexity of a particular process that this model is supposed to represent. For example, the first scenario is when a model is less complex than reality. Again, I'm talking about reality. Then usually we might say we've got like a flat model for a hierarchical process, and we may end up with something like very rough or superficial explanations. In the second case, we may have a model that is more complex than reality. So we can say maybe we've got a hierarchical model for a flat process, and we may end up with too detailed, too abstract explanations. Maybe the best case is when the model is as complex as the reality, when it's flat, hierarchical, and whether the reality is in terms of a flat or hierarchical process. And ideally, then we'll have what we might call precise or adequate explanations. Just to say a few words that although we live in a data-based world, we shouldn't forget that sometimes data that we have may not be reliable. It may be kind of missing data points. It may be kind of some contradictory data points. It may be incomplete, inconsistent, and so forth. So in this case, what we have to do is maybe try to use expert knowledge to make sure that we build a model which is really good. Because as you may have heard, something which has become like a joke in the field of AI and machine learning. I mean, your machine learning model or AI model can be only as good as your data. So if you've got very bad data, it doesn't matter what model you use. It will be garbage in, garbage out. I'm sure you've come across this term. So let's not ignore. We still have experts that can give us insight into data that is insufficient, incomplete, inconsistent, or unreliable. And then in some cases, maybe better to use what we call a hybrid approach. And let's not forget something I haven't put into the slides, that these days, people have started to use more and more artificial data. If you don't have sufficient, let's say, amount of reliable data to do your job, maybe you can try to, generate artificial data, which ideally has to be related to reality, and then you can use that data. And actually, there are some predictions that maybe in the near future, next few years, the proportion of synthetic data, will become much larger in relation to the real data we've got, although we've got large amounts of real data anyway. On this slide, I've tried to look at some very kind of well-known, well-established model kind of performance indicators, which are not only about AI. In any area, usually two main indicators we use are accuracy and efficiency. And quite often, these are two conflicting type of requirements, because if you want to improve the accuracy, this could be at the expense of efficiency. And vice versa. If you want to improve efficiency, it could be at the expense of accuracy. And here I've just tried to maybe conceptualize how I think maybe accuracy and efficiency could be affected depending on what I've described as model simplicity or explainability, and in the context of flat and hierarchical models. And again, just to mention that these days, to the best of my knowledge, we don't have any established quantitative indicators about explainability. What people use as a proxy for explainability or interpretability is the complexity of the model. I don't know, maybe that is what we've got at the moment, but ideally, and hopefully the academic community will come up with some more specific and more adequate indicators, because although complexity could be used as a proxy, it's not always a reliable indicator for explainability. And this is just one example. I'm almost finishing my presentation, by the way, just 2 or 3 slides left. With two kind of case studies, which almost everyone may be familiar with: mortgage application or job application. In what way a flat model could be different from hierarchical? Okay, so for example, for a flat model, usually the outcome for an application could be based on usually more inputs, but I made this simpler by just leaving 2 inputs or input features, like based on the income of the applicant and their assets. Well, maybe we could provide more useful explanation, especially to an applicant that's being rejected, by also including some kind of connection variables like repayments, because their ability to repay their mortgage depends on their income, and also deposit. Their ability to pay an upfront deposit obviously depends on their assets. So just one kind of example as to how a hierarchical model could provide a more useful and detailed explanation to a non-expert user. And the same applies to the job application example. Well, usually models, they generate an outcome based on, let's say, qualifications and the experience of the candidate, plus other things, but I've just kind of removed other things for simplicity. What we can do if you want to present that with a hierarchical model, we may be able to provide more expressive and more useful explanation by including these 2 additional variables like effectiveness and efficiency, because the effectiveness of doing any type of work, if you're successful with your job application, usually depends on your qualifications, whereas your efficiency in doing that work usually depends on your experience. This is maybe the last but one slide, which somehow summarizes the whole idea of explainable AI. Again, starting from the bottom and going upwards, we've got the real world that we want to model, and we want to capture some patterns and relationships there. And we've got some data about real world. Let's assume it's in a tabular format. And then we use an algorithm to learn a model, to train a model, maybe a black box model in most cases. But then maybe you want to also use what we call interpretability or explainability method to try to explain this black box model in order to inform the user. The only thing which is missing from this kind of flow chart is closing the loop, because I think that this still hasn't been done too much. And what is the purpose of closing the loop? We can achieve many more things, not just to explain the model, to explain the reality, but also on one hand to, for example, identify some bias in a model and try to suppress or mitigate this bias. These days, we may have models that may discriminate on the basis of ethnicity or gender or age, which are all protected characteristics. So they shouldn't be doing that, these models. Another thing that we can achieve is to try to identify maybe errors in the data, maybe in the labeling. So change the labels, retrain the model, and even improve the predictive performance of the model. And last but not least, we can also achieve this alternative reality. In other words, move the outcome into desirable direction for the better. So again, these are all kind of three very, hard to say, obvious benefits of explainable AI, which still need to be further developed and taken advantage of. And I'll just finish. Oh, sorry about that. This is my last slide with 3 books that I use for the module on explainable AI I'm teaching. So the first one is open access called Interpretable Machine Learning, a guide for making black box models interpretable by Christoph Morner. It's a great textbook. It's the main textbook for this module I'm using. It's not written in a very academic style, but otherwise I think it's very useful because each chapter or section finishes with advantages and disadvantages for a particular explanation method that is being presented, which is very useful for people who like to do research. They can just build on that. There are 2 other books. Second one is published by Springer, Explainable Artificial Intelligence, an Introduction to Interpretable Machine Learning by Eli Kamas and John Liu. It's written much better academic style. So if you think that you might like it, again, you might want to look at that as well. And it's, hard to say, it has a lot of breadth, but not too much depth. Bear that in mind. And the last one is Interpretable AI Building Explainable Machine Learning Models or Systems by A.J. Trumpy, published by Manning. Again, this is written in a more academic style, but it is kind of a bit disbalanced. It's kind of has too much content. Some topics like responsible AI and ethical AI, and maybe less content on other topics. So again, if you're interested, you may look at some of these books. There may be others as well, because this is a very rapidly developing area. Actually, the first conference, World Conference on Explainable AI, took place last year in Portugal. And the second one is taking place this summer in Malta. So they'll start organizing this every year. And almost all kind of major conferences organized by the IEEE, and other established societies, they've got kind of special tracks on explainable AI, panel discussions, invited lectures, tutorials, special sessions, and so forth. So I think this will be becoming bigger and bigger, and people are even saying that maybe it will become part of legislation. In other words, maybe in the near future, any company that wants to put a product on the market that has some AI in it, it will have to be accompanied with some explanations for the user, the non-expert user. So I'll stop here to allow more time for questions and discussion. Thank you very much for your attention.
Thank you for Alex for your presentation. So we will stop now recording and we will take some questions.